Welcome everyone to the third session of our meta learning workshop at IEEE. It's my great pleasure to introduce Lilian Weng. Her blogs are one of the main reasons I got interested in meta learning, the new kind of meta learning with deep learning and so on. And I think if you just look at the blogs, it's a nice transition. It's like a time capsule about how the field has evolved. I think it's a very interesting resource. Of course, nowadays she works at OpenAI and she does all kinds of interesting work on robotic manipulation. You may know her work from the robotic hand that plays Rubik's cubes, but she has done, of course, a lot more. And today she will talk to us about self-play for automatic goal discovery in robotic manipulation. Please take it away.
Shall I start?
Yes, you can start, and we can hear you now, indeed.
Yes.
Okay.
Everything's right.
Okay, sorry. I was asking for a thumb up or anything. I'm not quite sure whether. Okay. Hi, everyone. Really, I want to thank the organizer for having a workshop on meta learning, very interesting topics, and inviting me to give the talk here. I'm Lilian Weng from OpenAI, and I would like to share some work we did at our robotics team, and especially talk about some meta learning factors in those projects. I originally think I would mostly talk about our new projects, but I saw there are some quite interesting meta learning factors in our Rubik's Cube stuff that I want to share as well. So I tune my topics a little bit to be a bit broader. Okay. At our robotics team, one really big picture problems is how to develop the algorithm to power general purpose robots. Imagine a robot that can operate in the complex environment of the real world and carry out most tasks that we humans can do. And this demands the robot to be able to quickly adapt to the changing environments and interact with it effectively. Yeah, there's task, okay. And today I'm gonna talk about two projects where meta learning plays a key factor to help a single policy achieving amazing generalizability in environments or tasks that are not seen during training. The first projects, we trained a control policy to control a human-like robot hand, 100% in simulation, and deployed it on the real physical robots to solve a fully scrambled Rubik's Cube. We believe meta learning is quite important to trigger the success of sims to real transfer. And in the second projects, we trained a single goal condition policy to solve many different type of rearranged tasks on the tabletop. That is, you give various objects on the table, and then you show the policy a setting that you want to have. Then the robot gonna change all those objects to match your desired configuration. And during training, we have a special way to train it. But at test time, we were able to measure the zero-shot generalization to many on-scene tasks, including on-scene objects or on-scene configurations, and many semantically interesting tasks like setting a table, solving a puzzle. Okay, let's start with the Rubik's Cube projects. In this project, we're interested in learning dexterity skills on human-like robot hands, because to some extent, our environment is built around our hand. If you imagine how the facilities around you are designed, they're tailored in a way that your hands can interact with them pretty well. So potentially, if we could control robot hands really well, we could potentially automate many tasks that currently can only be done by humans. In the meantime, this is a very hard problem in robotics due to, for example, high dimensionality in the control space. In our case, we have those robot hands containing 20 actuators in 24 independent, not independent, free joints. And also the observation space, it's always very noisy and partially observable. Okay, our approach, we adopt reinforcement learning, and not surprisingly, to learn a policy to control this robot hand. And as we know, RL is very powerful, but often needs a lot of training data. They're eager for data, especially on policy algorithm. Like in our case, we use PPO, and that is quite data thirsty. And collecting training data on a farm of robots it might work, but it's a very fragile and expensive process to maintain and iterate. Instead, we decide to take the sim to real approach. That is, we train the control policy 100% in simulation. And then, because it is a really cheap way to collect theoretically infinite amount of data, and then we test it out on a real robot. Okay. However, sim to real approach might fail drastically because it is impossible to perfectly simulate a very complicated or complex reality world in simulation. And as a result, it may happen your policy is doing perfectly in simulator, but failed dramatically on the physical robot because it overfits to your simulation. And there exists a large unmodeled differences between sim and real. But eventually we did it. I'll just show a little video here. You might have seen it or not. So this is a video, this is our final delivery. This is a video of the hand solving the Rubik's Cube to a complete. It is playing at its normal speed. The whole process took about 4 minutes. I will only show the beginning. But one very interesting observation we had during many trials on physical robot is often the time the first few actions were the most dangerous one. They're slower and more unstable. It seems that the policy at the beginning was trying to adapt to the physical world, and but once the policy was able to achieve, say, 5 or 10 phase rotations or flip, it was often able to continue to complete the whole task. Okay, I'll stop it. It's available on YouTube. Our approach, we take this policy, especially we take a policy with a memory, like LCM, and train it over a large distribution of diverse environments. We believe that the combination of this policy memory plus a diverse training distribution can lead to emergent meta learning. In our setting, the policy learns to rapidly adapt its behavior to the physical world. That is actually an unknown dynamics if you're taking the view of what simulator knows about. And we believe this, and this rapid adaptation can be seen as a form of meta learning. We apply domain randomization to generate a wide distribution of training environments where a variety of attributes of both the vision and the physical dynamics are randomized. Previous work has shown really good success of better sim-to-real transfer with domain randomization. However, once the task complexity is increased to a level like solving Rubik's Cube, only using domain randomization is not enough, because in domain randomization, the randomization range for each environment parameters is predefined and fixed during training. If you set it too large, the model cannot learn or just learns way too slow. If you set the range too small, the policy quickly master it, doing pretty well, but it cannot transfer. So we have to do a lot of iteration process, like train a policy, try it out on physical robots. And this process of manually tuning the randomization ranges is very time consuming. Therefore, we came up with automatic domain randomization so that we can learn the good randomization ranges during training without the dependency on physical robots. Okay, so in automatic domain randomization, we maintain our algorithm maintains and grows a distribution over environment parameters. Step one, this is happening during rollout. We sample environments from this distribution and use it to generate training data. Step two, our optimizer would update the model parameters using data generated from this distribution of environment. Then we would measure how good our policy is doing right now and measure some performance scores and report it back to a manager node. And finally, we'll check those scores, see if the performance score is really high, it means the current configuration is too easy for the policy, we should expand it, make it harder. Otherwise, we shrink it because it might be too challenging. These steps are repeated until the end of training. It actually happens in parallel during rollouts. And at its core, automatic domain randomization implements a training curriculum that gradually expands the distribution over environments for which the model can perform really well. So to put them all together, domain randomization is fixed, but ADR has a potential to expand to cover a much larger and broader distribution of environments for training. And we are not quite sure whether the real world is somewhere in this plot because we cannot accurately measure all the physical parameters on physical robots. We believe meta learning is quite important for the things to happen. Quickly on the implementation note, we use a very simple factorized ADR. Factorized means each physical parameters is independent from each other. We grow or shrink them on their own. It does not consider correlations. Very, very simple. For example, this is a case when we try to tune the size of the Rubik's Cube. At the beginning, it's fixed at 5.7 centimeters, and gradually during training, as the model can solve the fixed size cube, we increase the range, meaning the policy have to be able to solve a cube from 5.5 centimeter to 6 centimeters. So it has to solve all those cases. This is interesting experiments we did to measure how important the curriculum factor is, because ADR is adaptively increase the distribution. At the beginning, we start with a fixed, very small, like a point, a fixed config of the environment. To compare those, we have a few baselines. They are trained with a fixed domain randomization ranges from the very beginning, and we don't update it. So it turns out the ADR version achieves higher scene-to-scene transfer much more quickly in time. And this, we have a hypothesis that the more domain randomization applied at the beginning, the harder it is to train a policy from scratch. So it's for very complex tasks like solving Rubik's Cube. If we set it the randomization too large, it might never learn because of lack of reinforcement learning signals. So the curriculum is quite important. Okay, we did a couple of experiments to showcase the sign of meta learning simulation. In this case, we run 10,000 trials in simulation with only cube flips action until 50 flips, up to 50 flips in one episode. And for each flip, we measure how fast the policy completed in seconds. That is the y-axis. X-axis is just the order of each flip. And the green line is the baseline on which we didn't apply any interactions. But on the blue curve, we applied interruptions at 10s and 30s flips, where we wipe out the memory of LCM cells. Interestingly, at those with those perturbations, we see a spike of time to complete, and after that, the time quickly decreased and back to the normal level, which means the memory of the LCM is quite important for the policy to complete the task fast and good enough. Another interesting point is the overall trend is decreasing, especially at the beginning, which aligned with what we observed on the physical robots, that the first few actions are always the most challenging ones. In another similar experiments, we applied a different type of interactions. So we actually changed the environment parameters in simulation. And we see similar spike right after perturbation, because the old strategies with which the policy is good at does not work anymore, given the changes in the environment. Then the network has to relearn about the new environments, and we again see the time and back to normal. Yeah. Okay. Yeah. For this one, we try to predict the environment parameters such as cube size using the policy memory, LCM memory, since we believe that the ability of the policy to infer this kind of information has a correlation with how diverse the training distribution is. And we did see a positive correlation. Okay. This is an experiment, this is a perturbation experiment we did on the physical robots. We tried to test how robust our policy is. And it's quite interesting, like we put on rubber glove on the robot hand. In other case, we tie two fingers together, or we just poking the hand with this giraffe. Quite happily, surprisingly, the policy is doing pretty well. It's not at its peak performance, but it's surprisingly robust. And all those perturbations, they do not exist in the training. in the training data. Okay. In another project, we are motivated to train a single goal condition policy that can solve any robotics manipulation task in a fixed environment. And to make it really concrete, the task we set up is a tabletop setting with a 1 UR arm attached with 1 gripper at the end. And the whole thing was fixed and attached at the edge of the table surface. And we can put any type of objects and any configuration on the table. In this environment, a task is defined as an initial state and a goal state given the same set of objects. And the policy has to interact with objects and rearrange them to match the goal configuration. The task is simple in its formulation, but it's likely to challenging a really wide of cognitive abilities when the objects become really complex or when the configuration becomes really complex. Anyway, like for example, in this case, in this rainbow puzzle, the policy has to understand what is a concave shape, as well as the order of the best or the correct order of putting things together. Following the ideas in Rubik's Cube, our approach here is to train a single policy on a very large and diverse training distribution. Then we evaluate our progress by testing this policy on many unseen holdout tasks. Importantly, I want to highlight or emphasize that any of those holdout tasks is not included in the training distribution. So we can really measure the zero-shot generalization performance. Which also means the policy has to learn how to do meta learning at test time in order to interpret the new task and adapt to solve it. One open question in this approach is how we build a training distribution that is rich enough to achieve such a broad generalizability. The training, as I mentioned earlier, the training task can be defined as an initial state distribution and a goal distribution. In this work, we just take an existing object database and randomly sample some objects and randomly placing them as a table on the table surface as our initial state. For goal distribution, I mean, you can imagine manually defined a couple of super interesting tasks like puzzles, making a tower of 10 objects, but this approach cannot scale. We need not like tens of thousands of different tasks. Then that's why we decide to do an automatic goal discovery process. Specifically, we employed a training framework called asymmetric self-play. This approach was originally proposed by Sukbodar et al. In 2017. And the original work only used a small proportion of self-play episodes in their main RL training to give additional signals. Like in their experiment was like some with 10%, 5% or 20%, depending on the task. But their main training process still happens on the target task. Unlike this work, we don't train policy on any of the target tasks, but instead we train it 100% with self-play, and then we test it as zero shot. In symmetric self-play, we have two policies. One goal generation policy, we call it Alice, and a goal condition policy aiming to solve whatever goal that Alice just generated. We call that Bob. Okay, so this process, this is like a sequential process. So first, we set up this random initial state. Alex will interact with it and produce a configuration at the end of its turn. That will be the goal for Bob. Then Bob will just try to solve it to, no, sorry. Bob will be given the same initial state and try to reach the same final state as Alice, which is the goal. Okay. At the beginning of this episode, as I mentioned, we sample initial state, and then we use Alice to generate trajectory. At the end, we have this last state of Alice as a goal for Bob, and then Bob will try to solve it. In the goal solving process, Bob will obtain a goal condition reward. That is a positive reward when objects matches both desired position and orientation. And at the end, Alice will obtain a positive reward if Bob fails to solve this goal. Otherwise, no reward for Alice. In this way, we encourage Alice to propose goals that are increasingly challenging to Bob, while Bob is forced to solve increasingly complex goals. Okay, one very interesting mechanism we adopt is we observe that one benefit of having this Alice goal setting step is we have at least one solution to the goal, that is Alex's own trajectory. And to provide additional learning signal to train Bob, we use Alex's trajectory as a demonstration for behavior cloning. We first filter out the trajectory, only select those that Bob fails, and then copy it to create, and copy it to create a goal condition version. And then we just use like very routine behavior cloning loss and jointly train that with RL loss. Because Alex's trajectory might not be optimal, like there are cases like Alex wandering around for most of the time and touch it at the end. So that's not something we want to learn all the time. So we introduced two designs to stabilize our Alex behavior cloning, short for ABC. First is demonstration filtering. We only collect demonstration for goals that Bob fails to achieve so that Bob will not be distracted from good strategies that he has learned for solvable goals. Another one is PPO style loss clipping. It has similar motivation as PPO, that we don't want to change the policy too far away from its original config. We use it for the behavior cloning loss. Okay, we can look at some experiments. Then the first set of experiments are conducted in block environments. We have 1 or 2 blocks, and we consider 4 holdout tasks corresponding to 4 different manipulation skills. They're pushing, flipping a block, picking up block up to the air, or stack them together. Here, the transparent objects marks the goal state. So first one, we just run PPO, train over this holdout task distribution. It turns out I cannot learn at all. It's quite challenging. Then we defined a slightly stronger baseline by introducing some manually designed curriculum. We found we haven't settled down with the good settings that can learn all the tasks. Here the dashed line is 1 block, solid line are 2 blocks, which are harder. And when we test our policy trained by asymmetric self-play, it can generalize to solve all of them in 0 shots. And this result suggests that asymmetric self-play can help reduce the importance of a good manually designed curriculum. We also find that asymmetric self-play often discover unexpected goals and solutions that are not actually, that haven't been tested in our holdout tasks. In this video, it discovered a goal of stacking 4 blocks, like in a tower up in the air, and tilting this block by very delicate balancing. And the Bob policy find the solution to that, which is pretty cool. In a set of ablation studies for ABC, we find that ABC is very crucial. First, we just disable ABC completely, and it cannot learn anything, unfortunately. This is like video comparing with without ABC training. And then we disable the demonstration filtering, which means we collect demonstration for all the goals, no matter Bob fails or not. In this case, you can see there's some noticeable instability in the flipping task. In another ablation, we disable the PBO style loss clipping. Overall, it's doing good, but it's in general slower on all the holdout tasks, and there a little bit instability in the middle of training as well. Okay, this is the last experiments we did with this. For this one, we want to test the approach up to its limits. So we use the ShapeNet, which contains, I think, 45,000 or 50,000 different 3D objects. We sample 1 to 10 objects from ShapeNet and randomly place as a table. And to test it, we defined a rich set of very interesting holdout tasks. And many are thematically interesting, like setting a table, put chess on the chessboard in certain orders, or 10-gram puzzle. And the learned Bob policy, it's able to achieve quite decent zero-shot generalization performance. I have like 2 tasks here, bow capture and table setting, but we have a lot more videos on robotics self-play GitHub.io. If you're interested, you can check it out. And this is a full performance of the success rate overall of the holdout tasks. Overall, it's doing good on many of them, but there's still quite challenging cases. For example, the goal capture requires dedicated handling of rolling objects and lifting skills. So that is hard. And rainbow task requires understanding of concave shapes. And concave shapes are pretty rare in ShapeNet. Stacking is hard. Stacking more than 3 blocks is hard because you need to understand what is order of your actions. And so overall, symmetric self-play can train a goal condition policy that can zero-shot generalize to many unseen tasks. It can alleviate the importance of manual curriculum, and having this behavior cloning from Alex trajectory is quite crucial. Okay, this is the final announcement. We open sourced the RoboGym package. It contains the simulation framework we used for both the Rubik's Cube solving tasks and tabletop rearrange tasks. It's quite fun, and for all the holdout tasks, you can use them in RoboGym. Okay, that's the end of my talk. Thanks.
Thank you so much. That was a very, very nice talk.